just make sure you stay here.
Yeah. So good afternoon, everyone. My name is Rajnish Kumar, and today I'll be giving a talk titled Linking Tensile Strength of Carbon Fiber Composite to the Strength of Single Fibers. It will be a talk about experimental, probabilistic, and a micromechanical approach. And I come from a division of wind energy materials and composite, Department of Wind Energy, Technical University of Denmark. So let's talk about the motivation of the work, or why we are talking about this. So since I come from a Department of Wind Energy, I'd like to present you a case study or a small topic about wind turbine blades. As you know, the world is moving towards green energy, away from coal-based or nuclear-based energy to a safer, less environmental degrading energy source. And the wind energy is one of the forerunners in that area. And to achieve that, the wind turbine blades are getting bigger in size. So here's an example. On the left image here about the size of a wind turbine blade. So as you can see here, it's comparing A380 airline to the wing, or the blade length of the wind turbine blade, how big they are in size. And I will call this blade to be, or the whole structure to be according to present time, mid wind turbine. Now they are increasing a lot in size. To the image here on the right, you can see a wind turbine blade, which is actually situated in the north, in one of the DTU test facilities in the northwest part of Denmark. Here you can see the wind turbine have a length of 75 meters. And one interesting thing to see here is the tip of the blade here, and and you can see here it's deflecting a lot towards the tower of the wind turbine. So one of the biggest challenge of designing such big structure is to have higher stiffness material of the wind blade to decrease the deflection. So the higher stiffness you will have, the lower deflection it will have towards the tower, and also to reduce the weight of the blade to have higher efficiency of electricity generation. And how we can achieve that. So in 2016, it was the world's biggest wind turbine back then, 88 meter in length. And it used a hybrid composite. As you can see here, this white part is glass, and this black lines here represent carbon. And what it did actually, if you see the graph on the right, is the length of the blade versus the weight of the blade over. And as you can see, this red curve here is a fit. And with this 88 meter length, it should come somewhere here across the red line, but actually it falls here. So because of this hybrid technology, the weight of the blade was lower than the expected weight it should have. Now, if we talk about the cross section of a wind turbine blade, how it looks like, and which materials, or which material geometry it's made up of. So if you talk here, this is rotational direction of the blade, and this is the wind direction of the blade. So the major load-bearing component of a blade is the spar caps here, which is made up of unidirectional material. There is leading edge, tail, and trailing edge. So I'm just showing you the unidirectional part, which is the major load-bearing part of a wind turbine blade. which is actually the point of discussion of today's talk, is only about wind turbine, the unidirectional composites. And as Yentel talked in his talk earlier, like when you try to design a hybrid composite, then to know the hybrid effect of what things you can have from those hybrid comes from the fact how good can you characterize your materials, whether it's carbon, glass, or any type of fibers you're using to make this hybrid composites, the baseline properties of those composites. So in this talk, we will talk about this ultimate tensile strength of unidirectional carbon fiber composites from 3 different domains. Single fiber domain, so I will try to discuss about single fiber testing, how to test fibers and what properties we can get from there. From composite domain, so I'll talk about static tensile test of a pultruded UD carbon composite having a fiber volume fraction of 67%, which is quite high, and fiber orientation factor of 0.9973, which is, you can say, is actually a really UD composite. And then I will talk about a micromechanical domain, how to connect these fiber properties and to compare it with the composite properties. And I will use Curtin's global load sharing model. And I will discuss this into much more detail. So let's first see like how the failure in fiber looks like. So if you take a fiber, so fiber has a lot of flaws on its surface, which could be either inherent flaws in the material during the manufacturing of it, processing of it, or during handling of it while you're testing the fibers. And these are the flaws which in the end results in the failure of these fibers. And how can actually imagine the fibers, how they fail? So it could be imagined as a long chain. The fiber can be imagined as made up of the long chain of small links, and it will fail at the weakest link here, and which actually makes the theory of weakest link theory, which was later utilized by Weibull to do a statistical analysis of those fibers. So that now if you can do many fiber tests, 100, 200, depending how many you do, and then every fiber fails at different strength levels, then you can determine a probability distribution of those fibers. And you can represent that probability distribution in this term, where this M is the Weibull modulus, which practically defines the spread of your data. Higher Weibull modulus will have lower spread in the data. Data will be close to each other. Sigma naught is the strength at that L naught length you are testing. But that's a given case of a fiber, because once you test a fiber, it breaks at a point and the test is done. But how it really happens in a composite now? And how can you actually connect this stochastic fiber strength into your composite strengths? For that, I'm going to discuss Curtin's global load sharing. William Curtin published a paper on theory of mechanical properties of ceramic matrix composite about this model, but actually this model can also be used for polymer matrix composites. And for this, what does the, I will try to discuss and take advantage of this board here. So I think the point comes, what is this term? Global load sharing. And there is another term. Local load sharing. And in Yentel's talk, he showed a diagram which was actually discussing about this local load sharing. And simple representation could be, if you imagine there is one fiber here, imagine there are 3 fibers in a composite, a very simple composite in a way, and you see a break here in the fiber. And due to this break, there will be some shearing action or whatever actions is happening here. So there is external load on this fiber in this region. And this forms the basis of global load sharing. And there are different terms to say about this, the stress concentrations around this region. And a more simple way to understand it is global load sharing, where it's not so complex. So fiber fails here, and all of them under stress condition act independently. So failure of this fiber at this point has nothing to do, in a way, it will not create any problems here. So you can analyze all these fibers independently, their behavior, to study the effect. So that forms the basic of a global load sharing model, which is easy to understand. Yeah, so here's a long list of nomenclature that will be used in the derivation I will try to discuss. So I think most of them are quite easy to, I think you already know a lot of them. I think if we start talking from this tau, then I will try to go the top 3 ones later. So tau is the interfacial shear strength that happens between the fiber and the matrix. R is the fiber radius, M is the variable modulus, EF is the modulus of fibers, and then these two, I think all of us know, the strain to failure of the composite and the ultimate tensile strength of the composite. I think the 3 terms here I would like to discuss, and which forms a quite important part in that derivation. So LC is a characteristic fiber length inside the composite at the fiber break. I'll try to show the image later and try to discuss more. Half LC is the slip length that exists at the fiber matrix interface from the break. And delta LC is the characteristic strength of the fiber at that length LC. So let's discuss like what happens when a fiber break inside a composite. So here you can see there is one fiber composite. So there is fiber in gray and white is matrix unloaded. Now we load the matrix and then you see a fiber break in the composite and the fiber is carrying the stress sigma. Now if you try to analyze this fiber break, what is happening? The fiber breaks and there is a tau, that is interfacial shear stress that develops on the break, and there is this length half delta C, the critical fiber length into this all. And now if we try to take a small element, these with this width dz, and analyze this finite element, so there is a shear force happening on the left of this element that could be just a tau into the cross-sectional area, and the increase of force towards the left, that is the d stress into the area of cross-section, and there exists a force balance between these two. And while balancing, we can find the stress as a function of z, that is 2 tau by r into z, that is the stress in the fiber at the position z. And at z is equal to half LC, that is a critical length, we get the simple stress is equal to tau by r LC. And this formula, I think, is very simple, which is also called simple linear load transfer from fiber break by Kelly and Tyson. And now we talk about like what is and since I have discussed like the fiber fails at one point when we test only single fibers, not in a matrix, it fails at a single point and the test is done. But what is the length of the fiber inside a composite that is relevant? And then we can use the same Weibull principle and find the probability of failure at a stress level and length. And the strength of the fiber, delta LC, at the length equal to the characteristic fiber length inside the composite break, LC, can be scaled using the Weibull parameters. And then we define what is the delta LC, that is the strength at this characteristic fiber length at the break, and which depends upon sigma naught, which is the stress or the characteristic strength of the fiber you're testing at L naught, Weibull modulus, tau, and the radius of the fibers. Now we talk about global load sharing inside. So when we apply a stress on a composite, that is a stress composites here. So fiber breaks, which is represented here, happens randomly across the whole composites. And then we take a reference line and we say, okay, we want to do our analysis here across this reference line. And this point here shows the LC, when the fiber from the fiber break where this tau is acting. Now, if we try to analyze just this magnified version of this, so through this reference line, we can take LC as the width of that reference line. So fibers can now all the fibers in the composite can be divided into two parts. One is broken fibers, which are represented here in the red line, and there are some unbroken fibers. So the unbroken fibers take the complete load, as you can see. But in broken fibers, there are two types here. If you see this number 4 here, says and Z is the distance of the fiber break from the fiber break to the reference line. So if this fiber break happens and Z is more than half LC, so the fiber is able to regain all its stress at the reference line, and it will take up the full load. But if this Z distance is less than half LC plus minus, so it will take up the stress as a function of Z, and it will not take up the full stress. So these are the two fibers which with the fiber breaks but take up the full load, and these are the fibers with the fiber break less than plus minus LC, which take stress as a function of Z. So if the total number of fibers in the cross section is N, then the unbroken fibers with distance Z greater than plus minus LC is N unbroken, and broken fibers can be represented like this. Now in the same cross section, we can simply do a force balance. So this equation represents the force carried by the unbroken fibers. We can do the similar expression for the broken fibers. And for those broken fibers, there exists, as I was talking about, the stress taken by them is determined as a function of the Z, the distance from the reference line we are talking about. And here's one of the assumption taken by Curtin. So stress in the composite can be represented by rule of mixture as this, and he's neglecting the matrix contribution. So he's only taking the contribution of fibers in this. So the average force by all the fibers on the reference line, that is the force taken by the unbroken and broken fibers, can be represented as a sum here. Now we can do a force balance, which is the force balance across the reference line. So here, okay, yeah. So force balance across the composite, and force is the unbroken fibers, and force taken by the broken fibers. I'll just go to the main equation, I think, depending on the time. Yeah. So the stress in the composite can actually be represented by this equation here. And this equation on the right is just the equation for this LC, you can say. So it depends on the fiber volume fraction, modulus of the fibers, characteristic strength of the fibers, viable modulus of the fibers, fiber radius, L0 is the tested fiber length, and interfacial shear strength. And if you have all these properties, you can actually predict the stress strain curve of the composite. Now talk about single fiber tensile testing and analysis. For this, we used semi-automated tensile testing machine and tested 150 fibers at different gauge lengths and and the fiber, the cross-sectional area was determined by vibroscopy method. So for one of the parameter we had was fiber radius or the diameter, and that we determined using this vibroscopy method. And here we have the data for around 1100 fibers, and it was determined to be around 7.3 micrometers. And we tried to compare it with the SEM microscopy results, which came out to be quite close. So this is the properties we will use in the modeling. Second point we needed was the modulus of the fibers. So the tensile, then we try to find tensile modulus as a function of the strain. And as you can see here for the carbon fibers, the modulus increases with the strain. So there is no particular number for that. So you need to define it at what strain level you want to determine the modulus of the fiber. So instead of using one modulus value, we put the modulus as a function of strain in the whole model. Then we need the viable properties. I will just come directly to this. So you need viable modulus, and what we call here is a strength length factor, which we determined to take advantage of all the fibers we have tested. And then we have this sigma naught m L naught average value that we are putting directly into the equation. And then we also need a composite to compare what we are getting. So for that, we use a protected X butterfly specimen. As Yentil was talking, it is a sandwiched material, actually a sandwich structure. So what we are testing is carbon fiber in the middle, and it is sandwiched between two glass layers to remove the stress concentration in the specimen. So we try to do some finite element analysis of this study to see how good does this protective layer works. As you can see here, the black line is the protective layer on the surface, top surface. And this peak you see here is at the end of the grips, there exists a stress concentration point. And the red line is the bottom layer of the carbon. So this protective layer is able to remove or absorb all the stress concentration on the surface, and on the middle carbon layer, there is no stress concentration. And the second thing is about the shape of this specimen. Yeah, the shape of this specimen. So because of this butterfly shape, the maximum stress happens in this gauge section of the composite, which initiates the failure here away from the grips. So then we have this stress strain curve for the composites, and then we try to see, okay, how does this model predict?
That's not possible.
I think it's just one slide, so it's almost done. Yeah. So now we compare this Curtin's model versus the experimental results. How does it fit? So now we see like the difference between the experimental result and Curtin model using a tau value of 54, which is the upper bound tau value we found is 28%. And this is just based upon the maximum strength of the matrix divided by √3. And if you try to do some a parametric study for different values of taus from 20, 30, and 40, then we can see how much it does it vary. And this model is able to capture the shape of the stress strain curve in a good way. And then I would like to conclude by saying, like, advanced experimental and data analysis method to determine the parameters for Curtin model, and Curtin model gives good approximation with overestimated value, and future work could be done using different material systems. Like if you want to see glass, then the viable properties look in a different way. Yep, and then thank you.